Good morning, everyone. So, myself, Mobidul Islam, and today, with my partner, Ankurjyoti Bhuyan, are going to present the BTech final year presentation titled as an IoT based smart healthcare system comprising of EEG and ECG signals. We have done this project under the supervision of Dr. Lasit Dutta sir, Professor Kandarbha Kumar Sharma sir, and under the co-guidance of Dr. Surajit Deka sir. So coming to the topics that we will be covering in this presentation. So starting from the introduction and motivation, we will come to the references of what we have taken for the presentation. Beginning with the introduction of our project. So what we are building? So we are building an IoT based smart healthcare system that combines EEG and ECG signals, and with the help of a machine learning or deep learning algorithm, it can predict abnormalities in the brain and heart respectively in real time. It is a more convenient way and a more portable way of a healthcare system, modern healthcare system. So what motivates us to do this project? So IoT-based smart healthcare system aim to revolutionize healthcare by providing real-time data for personalized and efficient care. These systems enhance remote monitoring, patient self-management, and reduce the need for costly hospitalizations. So these are the literature review. That means these are the papers that we have studied. We have studied about 25 papers, but we felt that these three papers and some more are relevant to our project. So by studying all the papers, we come to the research, some of the research gap we have found. So these research gap are there is very limited research on real-time analysis of EEG and ECG signal. The association of symptoms with ECG and EEG and their linkage to a specific disease has no exploration. And the most important, there is lack of effective and portable and cost-effective IoT-based EEG and ECG monitoring device. Problem formulation. So the research gap that we have found had to be solved out. So for that we have formulated out the problems. So beginning with the first phase that that we had done. So we had created a computer-based machine learning model to sense the abnormalities in the brain and heart. In the second phase, we have developed some deep learning algorithms, and with integrating with IoT, we have able to observe the abnormalities of a person's brain and heart in real time. So coming to the first phase, that is the computer-based prediction model. So in this phase, we have studied and collected pre-existing dataset, and we have trained the ML models, uh, and the models include SVN, KNN, RF, and we after that we have tested it for new features of the EEG signals, EEG and ECG signals, and we have got the desired outputs in a computer. So beginning with the EEG. So for the computer-based model, we have taken dataset of 40 persons, out of which 20 are normal and 20 are having abnormal. The dataset is of the set that there is 1280 rows and 31 columns. The 1280 rows depicts the signals of the persons, each person having a signal of 32, and the features every person has is 31. So by training and testing the model, we have come to the uh, accuracy of the models. So the highest accuracy is of the random forest algorithm with an accuracy of 67.07%, as the data are very limited, so we have managed to able to get this data on this accuracy only. But if we have augmented, or if we have collected more data, then we will be able to get above 90 or 95%. So these are the results that we have tested. So we have tested for a person suffering from abnormalities or a seizure. So the result can be seen here, and the graph of the abnormal person is shown here.
In the initial phase of our project working with ECG, we acquired dataset from Kaggle, where it includes data of nearly 1200 patients, 300 of each category. The categories were normal sinus rhythm, arrhythmia, congestive heart failure, and atrial fibrillation. Further, the raw ECG signals of these classes were processed using MODWPT, that is maximum overlap discrete wavelet transform. And coming to the ECG training and testing results, we considered three models: support vector machine, k nearest neighbor, and random forest, where it can clearly be observed that the highest accuracy was delivered by the random forest. So we took it a bit further and tried to predict a new signal the using the using the random forest classifier. And here you can have a look how we predicted it. And we also tried to generate the MODWPT transformed graph of different disease classes. In the right you can have a look.
So coming to the second phase of our project, that is the IoT based prediction model. So here we have implemented microcontrollers like ESP32, Arduino Mega, Raspberry Pi 4 for acquiring and processing of the EEG and ECG signals. We have also used sensors like MAX AD8232 for acquiring ECG signals, 32 electrode EEG cap for acquiring EEG signals, uh, MAX 30100 for acquiring the heart rate and oxygen meter. So we'll be doing this in the real time. So this is the overall methodology for the work. So for the ECG data, we'll be collecting the ECG data with the help of the AD8232 sensor, and after that we'll be doing the analog to digital conversion through the Arduino Mega 2560, and after that we'll process it in the Raspberry Pi or ESP32, and after that we'll be showcasing the result on a web server. Similarly, for the EEG, will be processing it in the PC, and the output will be shown in a web server. Coming to the EEG part of this phase, so we have acquired the signals from the EEG cap, and after that we have saved it in the .mat format so that we can use it in the MATLAB. After that we have pre-processed the raw signals in the MATLAB, and we have feature extracted the signal. And after that we have made the dataset of the signals, and we have augmented the data by add Gaussian noise. And after that we have implemented the models. We have also tested the models and showcasing the result on a web page. So this is how we have acquired the EEG. As you can see in the left, the person is wearing the EEG cap, and with the help of a software called EEG Lab, we have acquired the EEG signals. As you can see on the right is the graph of the 32 LED EEG signals. So coming to the pre-processing of the EEG signals, so we have done basically four analysis on the EEG signal, that is ICA, independent component analysis. So it basically separates mixed EEG signals into independent components to identify brain activity and artifacts. Coming to the second, bandpass filtering, it filters EEG signals to retain frequencies within a specific range, enhancing signal quality by removing unwanted frequencies. Coming to the third, Savitsky-Golay filtering. It smooths EEG data to remove noise while preserving signal features like peaks and trends. Coming to the fourth point, removal of the average trend. It eliminates the baseline shift or overall trend from EEG data to focus on various and patterns of interest. Coming to the feature extraction. So we have extracted 12 time domain features, including mean, median, variance, standard, skewness, kurtosis, zero crossing, etc. And there are several 19 frequency domain features, including power spectrum analysis, completeness power spectrum using FFT, band power calculation, the signals of the alpha, beta, theta signals, and many more. So we have tested two deep learning algorithms for the processing of EEG signals, that is long short-term memory LSTM and gated recurrent unit GRU. So before augmentation, the accuracy levels are very poor and the validation loss were very high as the dataset was quite small. But after data augmentation, we have chosen a dataset of 12,800, and after that we have got an accuracy of above 95% in both the models.
In the later phase, we move towards developing our, or we can say we move towards integration of models to hardware, where this is the block diagram representing the whole process. Our main ECG signal acquiring device is AD8232 sensor, which is being integrated with Arduino Mega 2560 for analog to digital conversion of the signal. We are collecting nearly around 140 points, that is 14,000 milliseconds per patient signal. We are then collecting it through PuTTY, that is serial transmission reception app. Using PuTTY, we are converting it to CSV format for further use. As the processing block diagram depicts, we tried two different ways for detection. One is deep learning algorithm using Raspberry Pi 4 and other is tiny machine learning using ESP32. Then we also developed a web server linking it to the models, where we can feed in this CSV formatted ECG signals and predict either the signal is normal or abnormal. Here is a glimpse of ECG signal acquisition and generation. Here you can clearly see that how the electrodes are being placed and the graphs of PQRST are being generated. I would also highlight the deep learning model graphs, their accuracy and losses. Here you can see the ANN model is much more stable comparatively to gated recurrent unit and the long short-term memory. Here you can see these bar graphs, where you can clearly observe that artificial neural network is having the highest accuracy and the lowest losses. These are the picture of the IoT integration with ESP32. And this block diagram is the supporting block diagram, show how we are inferencing ESP32 to TinyML. Similarly, this picture represents the IoT integration with Raspberry Pi 4B. And this block diagram supports how the process is being carried out. Now while working with these two models, we were able to draw some major differences with both hardware setup. If I talk about the Raspberry Pi 4, uh, we all know it's a bit expensive, as the Raspberry Pi is itself a whole computer in it, but the ESP32 is just an embedded system. So we can the Raspberry Pi can host the server in its itself, whereas the ESP32, the server is being kept at the main PC. Only the JSON file is being transmitted or received. but but in this both we can see that ESP32 has an edge and having a better accuracy than Raspberry Pi 4. Moreover, it is a bit fast than the Raspberry Pi 4, as it is running on TinyML algorithm. Moreover, the power consumption is also less. Uh, the the power consumption and battery voltage requirements are also less in ESP32. But when it comes to an edge of Raspberry Pi 4, we can clearly see that the Raspberry Pi is having an edge when it comes to the size, or the size is very large, and we can even store data in the Raspberry Pi itself. Moreover, we can also display add or add an external display to the Raspberry Pi 4. As a whole, the Raspberry Pi is also having its own benefit of being a system in its own. Lastly, I would also like to focus. I would like you to focus at our ECG web server, or the interface, where we are showing you that how we are going to feed the CSV formatted patient's data and predict either the data is normal or not. You can have a look.
So coming to the results, in the EEG part, we have chosen the LSTM model for prediction, as it can work on long sequence of data. We have integrated this model in the backend of the web server, and we have hosted the server locally. So as you can see on the left, it is the abnormal EEG detection, and on the right, as you can see, it is the normal EEG detection. So coming to the ECG, we have chosen the ANN model, as it is more simple in predicting the ECG signals. On the left, you can see the detection of normal ECG, and on the right, you can see the detection of abnormal ECG. Coming to the overall conclusion of our project, so for the working of the EEG signals, we have chosen the LSTM, and for the working of the ECG signals, we have preferred ANN. So we have also designed a computer and IoT integrated system to predict abnormalities in the brain and heart in a more portable way. So by doing a project, we can also have some limitation. So these are some of the major limitations in our project. First, coming to the first. So first, it is the IoT integration with EEG cap. The IoT cannot be integrated with EEG cap, as the EEG cap has 32 electrodes in each cell. Coming to the second point, we cannot direct signal integration with IoT. We cannot send the signal directly to IoT, as it requires a various changes in the signals, like ADC conversion, data manipulation, etc. Uh, Coming to the third, uh, we have not able to classify disease as it requires a large set of data. And foremost, IoT devices are very sensitive. It does not give results in every time we check it for some new data. So coming to the future direction, first point is the IoT advancement. So if anyone could do uh, some research on IoT, how it can implement on integration of computer and IoT in a more portable way, it can help in designing of a more compact and portable smart healthcare system. So by acquiring a large amount of data, anyone can predict disease abnormalities in the heart and brain. One of the foremost future direction is the business model. Our project aims to provide a business subscription for anyone who is living in the rural as well as in the urban areas. It means anyone can order or have a service uh, of the system of the smart healthcare system in a more convenient and portable way, and in a less cost effective way. So this is the overall working timeline of our project. So starting from the August 2023, so we have studied and acquired the EEG and ECG signals that have been pre-processed. So we have designed a computer-based ML model to predict the abnormalities in the brain and heart. So coming from the January 2024, we have studied about the IoT integration, the sensors required for acquirement of EEG and ECG signals, how we can integrate the signals with the IoTs, how we can develop the deep learning algorithm so that it can predict the abnormalities in the heart and brain in a more convenient way, and in a more uh, more effective way. This help this We have also uh, thought of doing it in the real time, and we have also acquired it. These are some of the references we have taken from IEEE and other websites of engineering publications. So thank you.